So far, we've looked at inference about a single variable, with either one or multiple groups with measurements on that variable. Next, we're going to transition into inference about the relationship between different variables. We call the relationship between variables an association. If certain values of one variable, like height, were more likely to occur alongside certain values of another variable, like age, we said that the variables were associated. It's unlikely that you would find a 6-foot-tall 2-year-old. Think back weeks ago to when we were talking about association between discrete or categorical variables. How did we look at associations between discrete variables all those weeks ago? We used contingency tables. Suppose we want to investigate the association between happiness and income level. Here we see some data based on the General Social Survey. We have an indication of whether the person had above average income, or below average income, and whether the person said that they were not too happy, pretty happy, or very happy. What does an association mean in this context? If there's an association between happiness and income level, then how likely it is for someone to be not too happy or very happy will differ for people with different income levels. On the other hand, if there's no association between happiness and income level, that is, if happiness and income level are independent, then how likely it is to be not too happy or very happy will have nothing to do with income level. You'll have the same chances of being not too happy or very happy no matter what your income is if the two variables are independent. But looking at the contingency table, it's a little difficult to know if it makes a difference to your happiness whether you're below average or above average income. We can't just compare the numbers in the table directly. Why not? The number of people in each income category is different. What did we do before to look for independence? We looked at conditional proportions. That is, we looked at the conditional proportion of people who are not too happy, pretty happy, or very happy, first just among those people who are above average income, then just among those people who are average income, and then just among those people who are below average income. Here are the conditional proportions from the General Social Survey happiness and income data. In this case, does it look like the two variables are independent? Not really. The chances of being not too happy are much greater for people with below average income, and the chances of being very happy are greater for people with above average or average income. If these two variables were actually independent, all the rows of the conditional proportions would be the same, like in this hypothetical table looking at the association between gender and happiness. Here, the conditional proportions in each row are exactly the same. It doesn't make a difference to whether you're very happy or not too happy, whether you're a male or a female. Now, even though it looks like happiness and income are associated in our sample from the General Social Survey, suppose just for a moment that these two variables are actually independent in the population. That is, the population conditional proportions look kind of like this bottom table. We don't have data for the entire U.S. adult population. We only have data for a sample of 1,362 adults. When we were dealing with proportions before, was the sample proportion always exactly equal to the population proportion? No, even though it was close, the sample proportion wasn't exactly the same as the population proportion. The same is true here with contingency tables. Even if happiness and gender are independent in the population, that is, even if the conditional population proportions are equal, the conditional proportions in the sample probably won't be exactly equal. We use samples to learn about populations, but we can't just look at the sample proportions to see if they're equal. How can we tell if two variables are associated in the population? Well, as before, we'll conduct a statistical test. What's the big idea of this statistical test? We'll assume, for the sake of argument, that the variables are independent, think about what we would expect to see in the sample if they really were independent, and ask ourselves how unusual what we got in our actual sample was if the variables really were independent. So before we jump headlong into the 5 steps of a statistical test, let's think just a bit more about what we would expect to see in our contingency table if two variables really are independent in the population. Think back to our days studying probability. We talked about events and the probability of two events happening together. We could rewrite the contingency table in terms of these probabilities. For example, the top left cell is the probability that someone has above average income and is not too happy. If the two variables are really independent, then how can we find the probability of having above average income and being not too happy? If the two events are independent, the probability of both of them happening together is the product of the two individual probabilities. So we can rewrite the entire table again, simplifying the compound probabilities into products of two simple probabilities. That is, for the cell of above average income and not too happy, we'll have just the probability of being above average income times the probability of being not too happy, where these two probabilities of being above average income and being not too happy come from the margins. Let's work this out for our happiness and income example. Here are the sample frequencies for each cell. If the two variables were independent, then the proportion of people in each cell would be equal to the product of the marginal proportions for the row and the column. First, we calculate the marginal proportions. For example, the marginal proportion of people who are not too happy, ignoring their income, is 12.3%, and the marginal proportion of people who have above average income, ignoring their happiness, is 21.3%. Then we can multiply these marginal proportions to find the proportion of people who would be not too happy and have above average income if the two variables really were independent. This proportion is 12.3% times 21.3%, which is 2.6%. Then, using the total sample size of 1,362, we can find out how many people we would expect to be not too happy and to have above average income in a sample like this one if the two variables really were independent. 2.6% of 1,362 is 35.77. If happiness has nothing to do with income, we would expect the counts in our sample to look something like this table. But even if the two variables really are independent, our sample won't be exactly like the expected counts, though they'll be close. The goal of our statistical test will be to determine how likely it would be to observe the top table, what we actually got, if we were expecting to get the bottom table, the expected counts if the variables really were independent. So first, our assumptions for the test of categorical association. We have three. First, we need two categorical variables. Second, we have to have randomization and the subjects need to be independent. Third, the expected counts in each cell need to be at least 5. Now we can move on to our hypotheses. The null hypothesis is that the variables are independent, and the alternative hypothesis is that they are associated, that is, that the two variables are not independent. There's a way to write this in mathematical notation, but it's beyond the scope of this course. In plain language, the null hypothesis in this example is that a person's level of happiness has nothing to do with their income, and the alternative hypothesis says that the chances of a given level of happiness depend on a person's level of income. So what about our test statistic for the test of categorical association? How have we constructed test statistics for previous tests? Well, we took the difference between actual and expected and divided by the standard error. So we'll follow a similar idea here. Our test statistic, that we'll call chi-squared, is going to be the actual count in a given cell minus the expected count in that cell, and then we'll take that difference and square it and divide by the expected count in that cell. We'll do that for each cell and add the results together for the entire table. With this kind of data, the standard deviation is related to the expected count. That's why we have the expected count in the denominator here. Notice that in this case, we're going to square the difference. The details of why are beyond the scope of this course, but the basic idea of the test statistic is the same. We want to look at the difference between what we actually got and what we would expect if the null hypothesis really were true. In this case, if the two variables really were independent. Now we have a test statistic. In general, how do we figure out how likely a test statistic would be? Well, we compare it to a sampling distribution. For previous tests, that sampling distribution was the normal distribution or the t-distribution or the f-distribution. Here, the chi-squared statistic has a chi-squared distribution. You may recall that the chi-squared distribution results when you add together the squares of several independent standard normally distributed variables. Like the t-distribution, the chi-squared distribution is characterized by degrees of freedom. The number of degrees of freedom from this sampling distribution of the chi-squared statistic computed from a contingency table is 1 less than the number of rows times 1 less than the number of columns. Rows minus 1 times columns minus 1. For the happiness and income table, We can compute a chi-squared statistic of 73.4. How many degrees of freedom will this chi-squared statistic have? Well, we have 3 rows and 3 columns, so we'll take 3 minus 1 and multiply it by 3 minus 1. That gives us 4. The p-value in this case is less than 0.001. So our conclusion is that we have evidence suggesting that happiness and income level are related to one another. The results of the test of categorical association tell you whether two variables are related. That is, it tells you if having a certain value on one variable, say income, means you're more likely to have a certain value on another variable, say happiness. Or alternatively, it tells you that the variables have nothing to do with one another, that your happiness has nothing to do with your income. But this test just tells you whether an association exists. It doesn't tell you anything about the nature of the association. Some other things you might want to know if you found that two variables are associated are the pattern of the association. Does having a high income make you happier or less happy? And the strength of the association. Does having a certain income make you really likely to be happy? Or does it affect happiness only a little bit? Let's start with the pattern of the association. When we're looking for the pattern of association, we hope to find out which values of one variable, happiness, are more likely when you have certain values of another variable, income. How can we find this pattern? Well, think about our test of association. We started with an expectation of what the contingency table would look like if the variables were independent. Deviations from the expected contingency table indicated an association. So to look for the pattern of association, we can look for the pattern of deviations in the table we actually got, the table with the association in it, from the table we expected to get if the variables were actually independent. These deviations are called residuals. A residual is the difference between the actual cell count and the expected cell count if the variables really were independent. Actual minus expected. This should be familiar from our discussion of regression at the beginning of the course. The residual will be positive if there are more people with that combination of values than would be expected if the variables were independent. And it will be negative if there are fewer people with that combination of values than would be expected. Now the residuals give an indication of whether each cell is greater or less than what we would expect if the variables were independent. But how do we know if the difference is relatively large or not all that large? We can compare the residual with the standard error to obtain a standardized residual, or z-score, for the cell, which puts all of the residuals on the same scale. The standardized residual for the cells of a contingency table is the actual cell count minus the expected cell count divided by the standard error, which is that expected cell count. This gives us an indication of how unusual the actual cell count is. Once we have our standardized residuals, we can use the empirical rule from the beginning of the semester to identify standardized residuals that are particularly unusual. These indicate where the association is. The empirical rule says that about 99% of observations are going to fall within 3 standard deviations of the mean. So standardized residuals greater than 3 or less than -3 are particularly notable. Here are the standardized residuals for the happiness and income example. Here we see that there are more people who have above average income and who are very happy than would be expected if happiness and income were independent. And there are also more people who have below average income and who are not too happy than would be expected if happiness and income were independent. So it looks like larger incomes are associated with greater levels of happiness. Notice the similarity between what we did here on the individual cell level and what we do in the statistical test of categorical association. We looked at the difference between what we actually got and what we expected to get if the variables were independent, and we compared that difference with the sampling distribution to see how unusual what we actually got was. In the statistical test, we added up all these differences to get an overall idea of where an association was. Then we looked in more detail at the individual differences for each cell to find the pattern of the association. But the principles are the same. We compare what we actually got with what we would expect to get if the variables really were independent. And we use the sampling distribution to figure out whether what we actually got was unusual. Now that we've taken a look at the pattern of the association, let's think about our final question. How strong is the association? First, what does it mean for an association to be strong versus weak? Association means, for example, that if you have above average income, you're more likely to be very happy than if you had been below average income. A strong association means that you're much more likely to be very happy than if you're above average income than if you're below average income. Conversely, a weak association means that you're not really that much more likely to be very happy if you're above average income than if you're below average income. So to determine the strength of an association, we compare the probability of being very happy when you're above average income with the probability of being very happy when you're below average income. We can do this with something called the relative risk. The relative risk is the ratio of two conditional proportions, and it indicates how much more likely one outcome is than another. If the relative risk is close to 1, that means the association is quite weak. And if the relative risk is far from 1, if it's either much greater than 1 or much less than 1, then it means that we have a strong association. How do you know which cells to compare? Well, whichever are most interesting to you in your study, and this can be informed by the pattern of the standardized residuals that you noticed when you were looking at the pattern of the association. Here are the conditional proportions for our happiness and income example. Let's look at the strength of association between happiness and income for people who are very happy. The proportion of people who have above average income and are very happy is 38%, and the proportion of people who are below average income and are very happy is 19%. So we can take the ratio of these two, 38% divided by 19%, that's 2.0. That means that you're about twice as likely to be very happy if you have above average income than if you have below average income. We could also look at the strength of the association for people who are not too happy. The proportion of people who have average income and who are not too happy is 8%, and the proportion of people who have below average income who are not too happy is 22%. So we can take the ratio here of 22% divided by 8%, and that gives us 2.75. So you're nearly 3 times as likely to be not too happy if you have below average income than if you have above average income. What about the strength of the association for people who are pretty happy? Well, the proportion of people who have above average income and are pretty happy is 55%, and the proportion of people who have below average income and are pretty happy is 59%. When we take this ratio, we have 59% divided by 55%, which gives us 1.07. That's pretty close to 1, which suggests that there's a very weak association between income and happiness for people who are pretty happy. In other words, you're about as likely to be pretty happy no matter whether you have below average income or above average income. So there are two important notes when we think about the strength of an association. First, a large relative risk does not necessarily mean a large risk. Let's look at this hypothetical example of the risk of cancer for people who eat fish or who don't eat fish. In this case, the proportion of people who don't eat fish but get cancer is about 1.2%, and the proportion of people who do eat fish who get cancer is about 0.3%. The ratio here of 1.2% divided by 0.3% is 4. So in this hypothetical example, you're about 4 times as likely to have cancer if you don't eat fish than if you do eat fish. But even though this is a pretty strong association, you're 4 times as likely to get cancer, but you still only have a 1.2% chance of getting cancer even if you don't eat fish, because the overall incidence of cancer is very low. So a large relative risk does not mean a large overall risk. Secondly, it's important to note that a large test statistic does not necessarily mean a strong association. The large test statistic refers to statistical significance, and a strong association refers to practical significance. So this is another example that statistical significance does not necessarily mean practical significance. Let's take a look at this example, this hypothetical example of the proportion of people who are religious or not religious, depending on whether they are male or female. In this first example, with 100 people, we see that the chi-squared statistic is 0.08 and the p-value is 0.78. So we don't have evidence for an association here. And that makes sense. The proportion of women who are religious is 51%, and the proportion of men who are religious is 49%. Those are pretty close to one another. What if we increase the sample size? What if we have 200 people instead? Now our chi-squared statistic is 0.17, and our p-value is 0.69, even though, in this hypothetical example, the conditional proportions are exactly the same. We can increase the sample size even more, to 10,000 people in each group. Now, even though our conditional proportions are the same, our chi-squared statistic is 8, and our p-value is 0.005. In this last table, it appears we have evidence for an association between gender and religiosity, but the conditional proportions are still the same. The strength of that association, if there really is one, is very, very, very weak. But since we have such a huge sample size, we have power to detect very, very weak associations.